Having learned about formulas in the previous lesson, we now turn our attention to how we name compounds. And we're going to focus in this lesson on naming binary compounds. So a binary compound, by definition, is a compound that contains only two elements. So nomenclature, or how we name compounds, is one of the things that the International Union for Pure and Applied Chemistry, or IUPAC, is responsible for. So they've come up with a system for naming inorganic compounds, as well as a system for naming organic compounds that you will learn about in more detail when you take organic chemistry. So the simplest case for an inorganic compound are ionic compounds in which the metal, so remember an ionic compound is formed from a metal plus a nonmetal, in which the metal has just a single common ionic charge. Okay, so that's going to be the metals in groups 1, 2, 3, and 13. You can see that group 1 is always plus 1, group 2 is always plus 2, group 3 and 13 are always plus 3. And then in addition to that, silver, zinc, and cadmium. Okay, so silver is also always plus 1. Zinc and cadmium are always going to be plus 2. So the way you name a compound like this is you just simply have two words. So you have the metal and then you have the nonmetal, except instead of naming the entire element, we stick an IDE ending on it. Okay, so let's look at some examples. The first one would be the formula LiCl, and the name for that is going to be lithium, the metal, chloride, okay, so that's chlorine, except we change the ending to "ide" and get chloride. Okay, BeO is beryllium oxide. Okay, beryllium is a +2 metal, oxide is a -2 nonmetal. AlBr3 is aluminum bromide. AgCl is silver chloride. And finally, for these examples, CaF2 is calcium fluoride. Okay, so you can see how calcium, being a +2 ion, requires two -1 ions, fluorides, to make an overall neutral compound. Okay, so these are fairly simple. You just have to remember the IDE endings. Okay, so what about ionic compounds where there's more than one common ionic charge for the metal? So these are going to be the transition metals, so the other metals in groups 4 through 12, and also the metals in group 14, which are tin and lead, down near the bottom of group 14. Not zinc, not silver. We talked about those already on the last slide. So what you can see on the right is a table from the textbook that shows the metals that have more than one common ionic charge. Okay, this is by no means an exhaustive list. One of the attributes of the transition metals is that they can take on many ionic charges. These are just the cases of the most common ionic charges. Okay, so for example, gold, Au, can be +1 or +3. Copper can be +1 or +2. Mercury can be +1 or +2. Lead and tin are both either +2 or +4. Cobalt +2 or +3. Iron +2 or +3. Thallium +1 and +3. Antimony +3 and +5. And then titanium +3 and +4. And then you also have certain metals that have 3 common ionic charges, chromium and manganese, and their charges are indicated in the table. Okay, so the way we name these, not only do we have to name the metal and the nonmetal, but we also have to show what the charge is on the metal. And the way we indicate the charge on the metal in the name is using a Roman numeral. And remember that the charge on the metal has to balance out the charges on each of the nonmetal ions. Okay, so our first example involves copper, CuCl. Okay, so in this case, Cl is -1, so therefore copper has to be +1 in order to have a formula where there's just one copper and one chlorine. So the name for this is copper 1 chloride. The 1 is a Roman numeral that shows that the copper has a +1 charge. Okay, the other common chloride of copper is CuCl2. So in this case, there are 2 chlorines. So as a result, copper has to have a +2 charge to balance the 2 1 minuses from the chlorines. And the name for this is copper 2 chloride. Now, you will sometimes see an older system of nomenclature where the lower charge has an us ending and the higher charge has an ic ending. So these are sometimes called cuprous chloride and cupric chloride. I didn't even write that on the slide because nowadays what I really want you to know is the Roman numeral nomenclature, but I just wanted to say that at this point in case you ever see such things. Similarly, you have ferrous and ferric if you have iron +2 or iron +3. Okay, another example with copper, this is Cu2O. Okay, so O is a 2- and there are 2 coppers. So therefore the coppers have to be +1 in order to get 2 of them to balance out an O2-. So therefore this is copper 1 oxide. Okay, moving to titanium. If titanium is bound to 3 chlorines, chlorine is of course -1, the titanium then has to be 3+, so we name this titanium 3 chloride. And titanium can also bind to 4 chlorines, and in this case the titanium is going to be +4, so the name is titanium 4 chloride. Okay, and then one example from this bottom part of the table, CrCl3. So this is worked out exactly the same way as with titanium. So there's 3 chlorines, they're -1. So therefore chromium in this case is 3+, and we call this chromium 3 in parentheses chloride. Okay, so that deals with ionic compounds. So what about covalent compounds? Those are of course the compounds that are formed between nonmetals. Okay, so the name of this is going to be a little strange in the beginning, but there's a number, one of the nonmetals, and then a number and the other nonmetal. This will make sense in a minute. But where I put number in here, that's what's called the Greek numbering prefix. And that's what you can see on the right hand of the slide here. So if you have just one of a particular atom, it's going to be mono. If you have 2, it's going to be di. 3, it's going to be tri. 4, it's going to be tetra. 5 is penta. 6 is hexa. 7 is hepta. 8 is octa, 9 is nona, and 10 is deca. Except in the first name, if you just have one atom of an element, you're not going to use a mono in that for that first nonmetal. The only times we use monos are for the second nonmetal. Okay? So the elements are named in the order that they appear in the formula. So the first one that appears in the formula is the first one that appears in the name, the way the formulas are conventionally written. And in case you're not familiar with what that convention is, the element listed first is usually the one that's further to the left or down on the periodic table. And it's frequently also the atom, the element that there are fewer atoms of in the formula. Okay, so let's get into some examples of what we would do here. So what about BF3? Okay, so we have a boron, we have 3 fluorines, so we need the prefix tri, and then we're still using the IDE endings here. So this is boron trifluoride. 2 words, trifluoride is 1 word, boron is the other word. Okay, CO. So this is carbon and an oxide of it, except there's just 1 oxygen. So this is carbon monoxide, which we have already met. A sulfur with 3 oxygens. Well, this is going to be sulfur trioxide, once again using the Greek prefix tri. Okay, an example that's a little harder, P2O5. Okay, so there's two phosphoruses here, so we have to use diphosphorus and then 5 oxygens, pentaoxide. And then we can do these the other way around also. In addition to coming up with a name given a formula, I can also ask you for the formula given a name. So we already talked about carbon monoxide. Well, then there's also carbon dioxide, and the di, of course, is telling you that there are 2 oxygens. So therefore, the formula is CO2. And then there are 2 other really, really important inorganic compounds whose names don't completely make sense according to systematic rules, but you still need to know them. One of them is ammonia, and the other is water. Ammonia has the formula NH3, and water has the formula H2O. Okay, and that leads me into a little bit of humor involving nomenclature. So if you were to do a Google search on dihydrogen monoxide, you will get lots and lots and lots of different hits. And this is just an example of something you can find on the internet. It's a button to ban dihydrogen monoxide because it is used as a preservative, solvent, and household cleaner. It is colorless, odorless. It is found in many lakes, ponds, and rivers. It is fatal if ingested in large quantities. Fatal with prolonged unprotected exposure to its solid form. Its gaseous form can cause burns. So this is some terribly hazardous chemical that we need to get rid of, right? Well, dihydrogen monoxide, of course, would be the proper systematic name for water. Except nobody uses that name, except weirdos on the internet. Okay, I've got another one for you. 2 men walk into a bar. One orders H2O. The second says, I'll have some H2O too. The second man died. What's going on here? Well, you may not know this yet, but H2O2, the number 2 as opposed to the word TOOO, is hydrogen peroxide, which, you know, some people put a little bit on cuts to disinfect them and it burns terribly. Well, if you drink that stuff, you're going to die. So that's, you know, the difference between H2O and H2O2. The number of oxygen atoms makes a big, big, big difference in the chemical properties. Okay, so in this lesson, we talked about binary compounds, just 2 elements. In the next lesson, we're going to get a little bit more complex and start talking about ionic compounds that contain polyatomic ions.